Awesome. Okay. So everyone, this is Max. He is joining us from ETH Zurich, where he works at the Systems Group and Efficient Architectures Lab. It's provided by Ana Klimovich and Gustavo Alonso. He has published and done a lot of work on data management for machine learning pipelines, deployments, data solution techniques, really the intersection of ML and data, which I think we all have some, at least, passing interest in here. He's in town for MLSys, and also because he won an award from ML Commons and won lots of other awards for his research because he's a very talented grad student and recognized as such. And today he's going to be talking about Mixtera, which is a data plane for foundation model training, which again, maybe seems somewhat relevant. So I will stop there and let Max take it away.
Thank you so much for the very kind introduction. Yeah, so I'm Max, and I want to talk about a little bit about what we have been doing at the ETH Group with Mixtera. And this sort of motivation came from our observation that there's a lot of infrastructure and tooling around model training and
who's that engineer?
Yeah,
Who's this person?
Yeah.
Right.
the intern from 4 months ago.
Did I laugh uncomfortably loudly?
Yeah, so we sort of wanted to address that issue. I mean, you already introduced me, so I'm going to skip over that. I work on ML systems at ETH, and yeah, basically I'm training large models right now. Sort of became interested in the space. Sort of attend like database, ML systems conferences, whatever. Sort of like the intersection. I think the community has really spread around those venues, and I'm very happy to be here and learn about what you guys are doing. It seemed really, really interesting. I want to learn more about what Datology is doing. So historically, where this project came from was from the Swiss AI initiative, which for academic standards is pretty cool because a couple of years ago, the Swiss government signed a contract with NVIDIA to get the latest GPUs in a couple of years. And then that was pre-LLM era, and now we have the opportunity to actually train models at scale in an academic context, which is pretty cool. So for this, we want to train some models open source in a reproducible fashion, and yeah, that's where sort of that meme came from. Okay, we figured there's not really data infrastructure for us to use in the open source world. Like how are we going to do data management, data ingestion, data mixing? That was sort of unclear when we started. And I mean, probably I don't have to preach to the choir, right? But LLM training data is structured typically in these sort of data collections. If we think about pre-training, we have different data sources, can be movie subtitles, can be Wikipedia, can be legal textbooks, yada yada. And then again, if we move or zoom into one of those data sets like Wikipedia, right, there's a certain hierarchy inside those data sets as well. Right, there is, for example, language, there's sensitivity, right? So you can think about it as this hierarchical structure or as a relational structure, right, with different properties. But typically, sort of the view is limited in most papers to, at the data set boundary, we consider, okay, where does the data come from, which data set, and that's sort of the property that we are most interested in. But beyond that, there's also other properties to consider in LLM training data and data set mixing on the data set level. Typically, people define a mixture on the data set level, right? So 60% Wikipedia, 20% legal text, 10% books, or something like that. And then they create a script to mix data accordingly and see how that mixture is forming. And in training, right? One example would be the pile. Which is not really used anymore, but a lot of mixing papers still sort of use as a baseline to see how their method compares to previous work. And they have a lot of different components, right? And then every component has different sub-properties like language, sensitivity, quality, and so on. And mixing really impacts model performance, as you probably know. And that holds true across different scales. So here's an example that might be interesting because here we compare a static mixture to a dynamic mixture. And when I say a dynamic mixture, I mean adjusting the mixture during training. So every training step sort of has a slightly different mixture that gets adjusted over time, instead of fixing your mixture at the start and then maybe you're having 1 or 2 or 3 different phases, like for example, OMO or small LM do. right? This is like continuously adjusting the mixture over time. And he's like one benchmark, and we can really see if
Sorry, how are you determining how the data mix changes? What algorithm are you
so in this case, it's called adaptive data optimization. That's one algorithm. There's others, for example, Aioli from Stanford. In this case, this is the Hella swag. There will be more and more experiments later on. But yeah, this is one benchmark on one algorithm for two different scales. Basically, what we find is across different scales, this dynamic mixing really helps in improving model accuracy without any further changes, right? So just by having the algorithm learn which mixture to use, we sort of can improve the model downstream performance. But when we played around with the algorithm, we realized, okay, deploying such an algorithm that dynamically changes the mixture is actually quite tricky, because most infrastructure today is built around having some JSON-L or Parquet files flying around, and then you just sequentially go through all of those files, read them, ingest them, and then load the samples. Maybe you shuffle them, but it's not really built for dynamically adjusting the mixture. So my understanding of datology, right, and I've only spoken to Bogdan around it, is that you sort of serve as a data selection mechanism. So a customer or somebody gives you a lot of data, and then you figure out, maybe let's say with 10% of the data, how to get the best model. So that's sort of my high level understanding of what you guys are doing. I'm happy to learn more. But in my understanding, you still have this mixing question after, let's say, the datology preprocessing pipeline. You still have, you filter out samples basically, but the remaining samples still have properties. So yeah, basically we end up with high quality data, less data, but still it's unclear, like in every training step, which data to choose.
It's a reasonable approximation. I mean, we also do some generative and synthetic approaches, and have some other approaches as well,
Yeah.
but none of which actually solve the mixing problem. And if anything, they probably make it more complicated because they add what you could consider to be like new sources, or sort of new, at least new dimensions, new features to the data that we have. So yes, we definitely have this.
Okay, cool. Yeah, and this so this is sort of again related to the Swiss AI initiative, thinking about how training data is stored. And in the worst case, people copy around data manually to training nodes in their cluster, right? Every user does whatever they want. Every time I want to try a new mix, right? I want to switch from 50% Wikipedia to 40% Wikipedia. I have to materialize everything, and I don't even know what test v3 JSON is supposed to mean, right? It's not really traceable. Maybe it's a little bit better. Maybe you have some form of distributed file system, right? Centralized file storage. You have some form of directory structure in your DFS that's sort of structured, but even this approach still comes with challenges. And this was sort of the first point in the Mixtera paper, which is it's really high engineering effort for data prep. And especially considering that typically ML people have to do this, right? So they're not trained in like data processing systems, right? Maybe the first time they encounter something like Spark or Beam, right? In a PhD might have worked with TensorFlow or something like this, but suddenly they are asked to write a data mixing script to mix together the different data sources. So that takes some time to get used to, and it's just also takes some time to run and then iterate on. And we don't only have the offline data pre-processing, but then we also have online data pre-processing, right? So something like mosaic streaming or Hugging Face, TIFF data. So this is really like still only limited supporting for mixtures, right? So typically this works by having different directories. So like this Wikipedia directory and movie subtitles, and then you pick one file from that directory, another file from another directory, and then sample based on those directories. But now if I want to define a mixture based on language, well, I'm stuck because my files are not structured by language, but by source data set. And of course, it also doesn't support dynamically adjusting the mixture during training, right? So thinking about the typical workflow, ML engineer writes some filtering script that filters the data, right? Or maybe even run some classifiers, some quality filters, or like quality annotation, all of that stuff, filters the data. In the end, we have to also commonly, if you train with Megatron, pre-tokenize the data, you materialize everything on disk, right? And then we're finally ready maybe if we use like an online data loader that supports it to sample based on the directories in training. And then we can sort of imagine like a big arrow that goes back to the beginning, because we probably don't do everything right on the first iteration. So it takes some time. And sort of related to this is that file systems seem to be the status quo for data management here. That sort of leads to storage overhead. So every time we rematerialize the data, we just have we require more storage, which is expensive. It's also not very performant. So if you think about, we only want to train it on English data and not on like French data or something like that, we have to linearly scan all of the files, right? Go through every JSON-L file, throw away the samples that don't have English in their language tag or something like that, because there's no index on a file system. And also, if you imagine training an LLM, let's say the New York Times, and the New York Times then sue you for training your model, and you need to remove everything. How do you even know which model was trained on which data? So that's sort of also quite hard to guarantee, because you didn't keep track of who accessed the files for which model training was. And last but not least, and that's sort of again related to dynamic mixing, is there are a lot of algorithms that adjust or that learn how to adjust the mixture during training. So it's Skillet and ODM. But there's also like this ADO algorithm that I showed at the beginning, as Ayuli. So yeah, this really changing how to do mixing, and it's hard to implement that in the training pipeline, because they also face like different constraints and so on. So it would be cool to have a system that just supports this as a pluggable module, basically. And then also thinking about mixtures beyond the dataset level. So what if I want to mix, instead of Wikipedia and movie subtitles, I want to mix on language. And then maybe also, within each language, want to have a one-to-one mixture between medical and legal texts, right? So we can mix more fine-grained than just the dataset level. And last but not least, multimodal models also coming up. So the question of which proportion to have, let's say, between image text data, like image text pairs, or only images, or only text in a Lava setup, right? That's also unclear. So we might also want to play around with how we mix together different modalities. So for all of this, there's not really infrastructure or a system. So we said, let's design a system that's sort of a centralized layer on top of your data set that allows you to just declaratively specify what you want, and then streams the data to your training nodes. So this sort of touches on the data loading aspect during training. Should also be lightweight. We talked to our data center admins, and nobody wants to maintain a Postgres instance or something like this, because then you need you need a database admin. You need to do the fine tuning, all of that, and all of that. So in the best case, we don't have a long-term running database. We want to support dynamic mixing, and of course, we don't want to bottleneck the training from data loading. So this was the previous pipeline I presented, and our idea was to build Mixtera by allowing users to declaratively specify what they want, right? So it's sort of like, I want 30% from dataset one in German, and then static filtering criteria and so on. And then Mixtera sort of hooks up these pointers to samples, and I will talk a little bit more about that in a second. So the idea is that Mixtera at the server side computes, these are the relevant samples that we want to use. And then every training node goes based on those pointers to the actual training samples and ingests them during training. So that's a basic idea.
Is this via like a distributed file system that you go to and get, or?
Yeah, so yeah, basically yes, but I get to that in a second. Yeah, so sort of coming back to the previous point, where's Datology here? In my understanding, it's sort of based on what Datology gave you, you can then declare your mixture and try around different mixtures. So sort of step afterwards. That is my understanding. So yeah, coming to your question, how does the data flow actually look like? So we have training nodes deployed in our data center. These are GPU nodes. We have a storage layer. We mostly use a distributed file system. Can probably also be like S3 or GCP or something like that. I don't see any fundamental challenges with that. We use the distributed file system. And the idea is to, first of all, instead of having just files flying around, to index all of your samples in a data collection. We use DuckDB as an index, right? So basically, the way this works is in Python, you specify a schema, right? So you say, I care about language, I care about source data set, I care about sensitivity, and you need to specify how to, given a file, extract those samples, right? So you need to sort of give a UDF for parsing a sample, and you specify the schema. We translate that to SQL basically, and then we go through every sample once and index that in the database. And then that sort of, we have a big overview of what data is available. And then for training, you submit a query, which gets forwarded to the system. And then the first part.
Sorry, who's a query?
A query? Okay, maybe
Does the query come from the training node? Where's the query come from?
Yeah, so maybe I should have shown this slide before. No worries, it's sort of my fault. So basically, at every training node, you
Pointing to the server. This is all the training.
This is on the training node, exactly. So on the training node, you define a query by saying, okay, I want to, first of all, filter out statically some data on some criteria. So for example, this time I only want to train on Creative Commons data, right? So that's sort of my base data set. So I first apply some static filters, and now I need to define a mixture. In this case, it's a very simple mixture based on just the language property. It's JavaScript and HTML, right? So we could also have more languages, right? JavaScript and Python, or we can have languages and license. So there's different ways of defining the mixture. And then the chunk size basically, I come to that in a second, that defines how many samples each chunk contains. So that's executed on every training node. We then need some hyperparameters about the training, how many data loader workers you're using, also like how many tensor and data parallel nodes and so on. Basically, how does your training setup look like? That's typically given by the training framework. So for example, Torch Titan or Nanotron. And so you need to tell us, okay, what are your static filters? What is your mixture? And then what are your training hyperparameters? So we can distribute the data correctly. And then everything else is sort of encapsulated in this Mixtera Torch data set. If you want to use like something like TensorFlow or JAX, right? There's a different.
Though. That's serious. That's funny.
You can also use a different abstraction, but in this case it's Torch. Yeah, so this hides then all of the networking and query execution stuff. So this is sort of what the user sees, what the training script contains. And then everything else is hidden in the Torch data set, which you can just use as a standard Torch data set, right? As a training data loader, you can iterate over it.
So sort of like a dynamic mixture would be essentially the same, just like a capacity dynamic mixture.
Exactly, you have a dynamic mixture object and you need to specify the algorithm, right? So that would look like dynamic mixture. You have to have some starting point, so you still need the static mixture as the starting mixture. Can also be like inferred mixture, which means just a natural distribution of data inside your database. In this case, you don't need to specify anything. And then the mixing algorithm, something like ADO or ODM. So that's executed at the server. So this is at the training side. And now let's go back to.
One question I have is, so if you have multi-nodes, do they create a copy of the same parameters at each node, or
Yes.
is it managed
Like in the training script, and it knows what rank I am. And stuff.
Exactly.
Yeah.
So while it looks like the same, right? So it's sort of you don't need to think about which is node 0 or something like that. But inside the Torch data set, okay, we get our rank in the training setup, and if we are not rank 0, then we're just waiting for the server to tell us the query has finished executing. If we are not 0, we actually execute the query with the server. But that's sort of hidden. As a user, you don't really need to think about who executes what.
The same data is never on two different nodes.
Yeah. So at this point, right, up until you specify the data set, no data has been transferred. As soon as you instantiate the data set, you execute the query, and then still no data has been transferred, and then we slowly, streaming in a streaming fashion, start transferring the data. So it's not you pre-compute everything, but you stream on the fly, right?
And do you log metadata, the same metadata on all the nodes, and then you split that between workers? Or
What do you mean by log metadata? Which sort of metadata?
for example, do you load some kind of metadata about the all data you have into all the nodes?
No.
Or
No.
Sorry, I read the paper already.
I believe you.
No, yeah. So that all stays on the server. I think it will become more clear when I go through this. So we index all the data. So the query is basically just a representation of this code that you've seen on the previous on the other slide. So we pass that and we execute it. First, we execute the static filtering. So what we saw before as the Creative Commons filter, right? So that's sort of the base data, all the data that we can potentially use during training. So that's what we call a query result. Can you imagine this as a big cake, right? So that's all the cake we can eat. And now is where the chunks come into play. Basically, a chunk is a piece of cake that we eat during training as like a fixed size number of samples. So every chunk contains pointers, let's say 1,000 pointers to your data. So chunk would say, please go to file abc.jsonl and read samples 10, 11, and then 15 to 20. So the idea is to use as much consecutive data as we can to avoid, because most people still use JSON-L and Parquet, which are optimized for sequential reading. So we want to optimize for that, right?
Are there other formats that are not optimized for sequential reading?
I mean, web data sets, sort of, I guess, but still.
We don't talk about tar files.
Yeah, okay, but then yeah, there's not really. I'm not aware. Like
I wasn't either. I was just curious.
Yeah.
Okay. Cool.
So yeah, and because we want to say like a fundamental design decision that we made is we don't want to shuffle your data, right? So it could be that if you mix on language and all of your language is clustered within a file, that's great, right? Because we can, if we just want to read English, we can read consecutively a lot. But if the data is not clustered by English, we have to read one sample, then skip a couple of them, read the next. So that's something we try to optimize for in like the engineering wise, but we don't want to shuffle around your data because we don't want to create a login effect on Mixtera and make it more easy for people to start playing around with it. It's sort of a trade-off. If you have more control over the data, right, you can optimize the data layout.
If you work, say, at a company that generated pre-training data sets,
yes,
you control the data.
For example, if you know what mixture people use,
and we're in fact interested in locking people in.
yeah.
That's hypothetically speaking.
For example.
Okay, I'm just curious. It's interesting. Academic conversation, right? It's very interesting.
All hypothetical.
Of course.
Then you exactly. So these are chunks, right? So chunks contain pointers to samples. These sort of ranges in files. And then these chunks get transferred over the network to the training nodes. So that's what's being transferred. These pointers. So the training nodes don't know about the metadata. They just know, okay, I need to go to this file and read samples 10, 11, and 15.
How do you transfer? What is the serialization? How do you transfer a chunk?
So it's literally just pickling a chunk, because that and it's not a very expensive operation. It's just a dictionary in that case. So that's not. Also, the chunk generation, right? It might seem crazy, maybe at least to VLDB reviewers, to have one central server generating the chunks, but the algorithm to cut off those pieces of the cake, it's really like milli or nanosecond scale, right? It's not very expensive to generate those chunks. You just have to ensure they follow the mixture, and then you can it's not the super complicated algorithm or anything like that. We have it in a paper. I can talk about it if you're interested. But like all of this, like the chunk generation, this chunk serialization, the network transfer is way faster than transferring files over the network, like the actual data. So like the training, right? If you need to optimize something, it's like the file reading and file transfer over the network. Yeah. So basically,
I ask something here before we move on. Maybe you already explained this, but I mixed it. So you request some queries or maybe some data points, right?
yes.
So where does that happen actually? In the step of deciding what IDs or what training examples you want to query?
Yeah.
Is it on the training node or?
Yeah. So every let's say the rank 0 training node, the rank 0 training node actually sends the query over the network, right? So it's coming from rank 0. All of the others are just waiting for the query execution to finish. And the server then actually decides, okay, based on that query, I need to go to file1.jsonl or .parquet and read samples 10, 11, and 15. So that's happening at the server side. And
here you assume that you have a black box that will decide for you what samples to request. And there could be any data mixing algorithm, right?
So if I'm not sure I get the question correctly.
Let me repeat again.
Yeah.
So let's assume you have a blog post that will tell us, hey, now I'm training the model and I need to feed these examples into the model. These examples could be based on any algorithm, could be based on the language or based on the quality. So do we assume that the system here is agnostic to this algorithm, or how exactly we select what examples to query? Or?
So the system is agnostic to the mixture.
Okay.
So the user can say, I want to mix based on English or based on data set or based.
And then can the mixer also be a data filter?
Right. If a domain has a weight of 0, right, it could also serve as a filter. But
You also have a filtering mechanism.
yes, we also have a filtering mechanism, right? So here we only select Creative Commons data. So it's sort of like the base data that we use. So you can, I think, that's why I sort of try to use this cake analogy, right? So the base data is like the entire cake, and then one chunk is one piece of the cake, and the server decides which piece to cut. And that's sort of like an algorithm that we use to just it's not a super complicated algorithm. Maybe I should have put it in the slides. It's basically just based on the mixture that the user specified, let's say English and German, right? You check how much data do I need still in this chunk. Let's say I need 500 English samples, and then we just linearly go through all the files that we have and ask the file. It's a lot of abstractions that build on top of each other, but every file can give you consecutive ranges of samples according to the mixture. So the server knows, okay, I need 500 English samples. These are all the files that contain English samples, and then we use 10 samples from that file, 20 from the next, and so on. So it's sort of an algorithm inside the server that creates chunks based on a mixture. And the core fundamental abstraction is the mixture representation.
And it's doing chunking for all the training nodes? Or
Yes.
the one? So
Exactly. So the server is like a centralized thing that creates chunks for all of the training nodes. And let's say you have pipeline parallel nodes or tensor parallel nodes. Commonly, the training frameworks, they need the same input, right? Or like a 0 input, but for example, with Torch Titan, they only need the same. That's what a chunk distributor is for. So every
pre-computing multiple streams and lines of falling.
yes, exactly. Yeah, it's not pre-computing, but it's caching the chunks, right? So if this chunk is needed by, let's say, 2 nodes, that the serialized version is cached in the chunk distributor and sent to all the nodes that need it. With data parallelism, then 2 data parallel nodes basically get 2 different chunks, so they get different data. Yeah, so the parallelism is sort of handled at the server. Yeah,
So we're kind of a hyper engaged audience. Sorry about
no, I love it. It's completely fine.
So you mentioned that maybe we just need 3 samples, but do we transfer the whole file? So let's say we just need 10, 11, and 15, but the Parquet file has maybe 100 rows. Do we still transfer the entire file?
Yes.
And is there a way to optimize that?
Yeah. So
If you just pre-compute the data and structure it in an optimal way, there would be.
Exactly.
But they don't do that. They don't solve that problem.
Exactly. So if you have a file, right, if you pre-computed your files in a way that you don't need to touch certain files, right, then we can avoid that. Otherwise, the only way to avoid this is if your DFS driver somehow manages that for you. So the way we, for example, in JSON-L do it is we skim, or like we skip several lines or something like that. Oh no, wait, JSON-L is a bad example. If we have like a memory map file and then we just go to a certain byte range, right, and your DFS driver avoids transferring the other bytes, that's a way to do that. But for everything else, we just need to, especially JSON-L is where we don't have an index in the file.
Parquet has metrics for this, right? Like you can skip row groups and stuff.
Yes, exactly. So for Parquet is a bit tricky because it depends on how the file was saved. So yeah, what we do is we pre-compute the relevant row groups. So if we know we need samples 15 and 100, we can compute in which row group they are in, and then we only need to go through those row groups, but we still need to read the entire row group sequentially. So it really depends on how your file was saved.
So the tokenization is happening on the node, on the fly.
Yes, it's a very good question. And you can also have pre-compute pre-tokenized files. In this case, you don't need to do tokenization. But if you have JSON-L files, like we did, then you read the files here, and Mixtera also takes care of tokenization. Or other computations, like let's say you do multimodal training, you need to do image decoding, image flipping, image cropping, all that stuff. Bless you. Right. So that's sort of happening on the fly.
Related question. Oftentimes, almost always, unless you get extremely lucky, there's not a one-to-one mapping between, like for LLM, your context window and the length of a document.
Yes.
I imagine you could, like, one design choice here would be like, okay, you're going to basically like pre-chunk all your files, if they are larger than whatever your context window is, to be that at the maximum, and then you're treating that as a like individual sample.
Yeah.
But otherwise, like if you have like excess tokens beyond your context window that you're getting from a single sample, do you just lose those during training? Because it doesn't seem like there's a way to keep track of like, I have extracted this much of this file and already used that, but I haven't used these remaining tokens, which could be used for something. So I'm curious, basically, how do you handle the like ragged, ragged samples?
That's a very good question. It caused me a lot of headache.
I imagine that's
So the chunks are generated on a sample level per file. So if you have very imbalanced samples, which for example is the case in the file, where books are very, very long, and then you have IRC messages, which are very short. So the way we do it is we generate a chunk based on samples in the file, so they can be very imbalanced. And then at the training node, so on each node where we do tokenization, so this only works if we do tokenization inside Mixtera, right? If you handle tokenization, we cannot take care of that. But if we handle tokenization, we still okay, so every client is aware of the mixture, tokenizes the data, and for every mixture domain has sort of a buffer of tokens. So if you have excess tokens, like for books, you might lose some tokens in the end, but we guarantee you the mixture on as long as we can. Basically, we can do it in either like a best effort mode, which we call it. So in the best effort mode, we use all the tokens, but that can lead to the imbalance. In the strict mode, as soon as we cannot guarantee the mixture anymore from that chunk, we say the chunk is done. That means that you lose, in case of a book, you lose a lot of tokens. So that's why we say, okay, you don't need to have perfectly balanced samples, but it would be good if they're sort of balanced to minimize the waste. But so like books that like thousands of words versus IRC messages is sort of like the worst case scenario. Yeah. But if sort of like split based on your sequence length or something like that, or twice the sequence length, that's fine. But the system guarantees you using it just buffers the tokens, and then if you have either if you have like too little samples, we can do padding or repetition, or if you have too long samples, then we cut off after a certain point to guarantee the mixture.
Cool. So Max, are you saying that the actual data set, that force data set object, guarantees the mixture in terms of tokens?
Yeah.
But then upstream, it's doing the mixture in terms of sequences. And
yes.
So there's sort of like a reconciliation that's happening on the training node.
Exactly. If we do the if Mixtera handles the tokenization, it could be that some data inside the chunk is unused because of data imbalance. And then sort of the next chunk will need to be streamed in a little bit early. You can always say, I don't care about imbalance on the token level. I just want to have it on the sample level, like roughly, because all of this is stochastic anyway, right? It probably doesn't really matter if it's like 89.5% or something like. So that in the book's case, it matters.
And you cannot carry over like the leftover chunks, the leftover tokens to the next chunk.
I mean, so that's something fundamentally, I guess you could. It's something not like I didn't bother engineering so far, but yes, you could have something like a leftover buffer from a previous chunk. But so you can imagine what happens inside the training node is like a nested for loop. you have a loop over the chunks, right? So for every chunk the server gives me, do something, and then for every chunk you loop for every sample in the chunk, and then right, the chunk is sort of the cutoff point, right? After one chunk, you forget about the previous chunk, so to say. Yes, so that's sort of why it's not straightforward to do this, because the system is not engineered to have some form of state like across chunks. But I guess it would be, with some tricks possible.
Just as a time check, we have about 7 minutes left.
Okay.
I know we've been asking.
I have another hour worth of questions.
Yeah.
I mean, I'm happy also to chat with you guys one-on-one, but I totally understand if you have other meetings or whatever.
Yeah, great, please.
Yeah.
Can I ask one more quick question?
Sure.
I know we just like
Yeah.
so another thing that can happen, or unfortunate scenario for training models is that NVIDIA hardware is not very reliable.
Yeah.
And if you train a large enough model, you're almost guaranteed to have one GPU fall out and then have to restart your training.
Yeah.
How do you deal with presumption and like determinism and statefulness? I mean, there's some amount of randomness here, but ideally, when you restart the run, you don't see the same chunks you just saw for the previous.
Yes, exactly. So we support checkpointing. So every time you do a model checkpoint, you can also send a checkpoint request to Mixtera. And then if you resume training from a checkpoint, Mixtera can also resume exactly from the same data. So the way, so basically you have we guarantee determinism in terms of the samples. And the way we implement it is basically we keep track. So we persist the state of the cake at the time you do a checkpoint. And then because the algorithm we use to cut off the pieces of the cake is reproducible or deterministic, you always end up with the same data. And same is true for the client side. So basically we guarantee it's deterministic on the server side to generate the chunks. And then at the client side, given a chunk, the reading is also deterministic. So it's random, but it's shuffled based on properties of the chunk. So in that case, it's random but reproducible with a fixed seed.
Nice.
That makes sense. Cool. But yeah, so I talked about user interface. I like the way in the paper we evaluated this is we talk a little bit about model accuracy to convey the database community a little bit an intuition on the role of mixtures, and of course the question, does it bottleneck training? And here this is this adaptive data optimization algorithm. The idea is basically to have a per domain scaling law in that algorithm. So for every domain, that can be Wikipedia, movie subtitles, we understand we want to learn if we would train on another sample, how much would that decrease our loss? And then they do some approximations to basically derive how to calculate the next weight of the mixture based on that. Here's an example, the 6 largest domains in the pile, sort of how the algorithm learns over time. And here you also see Mixtera's sort of best effort mixture approach. So here we run out of data for books. So that's sort of because we split it very basically what you said, because we didn't do a proper split, right? So every sample is quite big. We lose some data in books free. So basically I read this with splitting the books domain, and then it doesn't run out. But in this example, the books domain, we run out of data, and then Mixtera sort of proportionally upweights in chunk generation the other domains. And you can see, so this is what you see actually at the client side, right, in terms of tokens.
What do you mean by you run out of data here?
So you just don't have books data anymore. You don't have a sample that's tagged.
You finish an epoch or?
No, basically, yeah. So you could think of it as an epoch on the book data set. So you could also start over again. That's another alternative for that domain. But you just don't have, right? We want to train for 30,000 steps, but we don't have enough data from the books domain to keep training.
There's no nuancing data.
Exactly.
And this is the choice of Mixtera, or is it a choice of the ADO
To
output? To downweight it?
I mean, the ADO algorithm would like to continue using the book.
I see.
But Mixtera says
You hard coded that you should only see sample once.
yes, basically. Mixtera says there's no more data, and then the way we handle it right now is either to stop training or to upweight the other domains proportionally.
Oh, but you cannot replay the same data, right?
It would be possible, but Exactly. Like at
It's
least
just an option. It's a design choice for you.
exactly. So you could easily implement this and then make it like a configurable option. We wanted so far we didn't need it, so it's not in the system. But yeah, that would be possible. At least for simple mixtures. If you start thinking about the case where you mix on at least I think 2 or 3 properties, you can construct a case where a sample would match multiple domains, right? So a sample can be English, Creative Commons, and sent from Wikipedia, and then it's unclear what resetting means. But at least for these simple mixtures, it's you can also like restart the book's domain.
How do you even handle, like if you're saying I want 20% English and 30% Creative Commons, and then I have a sample of both, does that count towards both? Does that count towards one?
Yes. So that's part of the chunk generation algorithm. So we have something called a mixture key, and a mixture key is a combination of the property, which is language, and a value for that property, like English or German or something like that. And we sort all of our data that we have so by their mixture keys. And then we do key matching. So basically, the mixture key can match another mixture key if it fulfills that. So if we have a sample that's English Creative Commons, or we have a sample that's English and MIT license, and we look for English, both would match. And if we have another key that looks for English and MIT, it would only match the English MIT key. And that sort of is the way we do it by matching, looking for which samples match the key. And now those keys define an order, which allows us to use the more specific samples first, and then rely on the more general samples only if we don't have a specific sample. So yeah, the idea is to use the more specific samples first, because the other more generic samples, the sample that is just English can be used for any license. So we would prefer to use the MIT license samples for MIT.
But as a user, you have to be careful then, because you might implicitly, if you have certain data, you have a lot of English MIT, you might accidentally upweight English by adding a higher filter percentage to MIT.
No, you wouldn't upweight, right? So you always have a certain guarantee. Like you always have the same proportion of English. It's just a question of you would implicitly have a more MIT license data. So if you think that impacts your downstream model, but that's again also something that we complain about. But my answer to this would be if you have a property that matters, you could put it in your mixture. Because if you don't put it in your mixture, we assume all English data, if you just mix on language, all English data is equal. But if all English data is not equal, you should have that in your mixture. Because we cannot know in which way it is unequal. If MIT is better than Apache license or something like that. Okay, so here's just some more numbers from this Ardo run on a 3D model.
You do not have to convince us.
Yeah,
data mixture.
Exactly. So I think this is sort of like maybe dynamic mixing, right? Because you said you don't touch the user training loop. But yeah, exactly. Like it helps, right? And we also just, we here. I'm not an expert on VLMs, but nevertheless, we wanted to see if fine tuning on different mixtures also has an impact on model quality. Turns out it does. It didn't surprise me, but basically, I think there's a lot of potential for mixing, also like from a research perspective for VLMs. I saw a lot of papers for LLMs, not that much for multimodal models. It's sort of like
yes, and for multimodal, it's also like you often naturally have more mixed data sources for VLMs.
Yes.
So it's more present of a question, but yeah, it seems like the multimodal research is starting to catch up in terms of thinking about data mixing.
Yeah, and here you not only think about which data source the data comes from, but also like in what proportion different modalities you show to the model, especially for like model architectures that allow like let's say mixing image only with image text or text only. That's sort of also the trick question, I think, in what proportion to show this. And it seems
the ADO algorithm generalizes to multimodal as well.
I haven't tried it. So this is not ADO, this is just static mixtures. I see. ADO basically works on token count. I wanted to try it, but it could be because I think with images you have a lot more image tokens than text tokens, right? So you sort of need to account for that.
So here you did like a grid search over the mixtures.
Yes, here's just like randomly generated 256 mixtures.
I'm so sorry, like I'm stupid, but like this is outside of the range of noise, or like what am I seeing here? Like what I mean,
yeah.
If I generate 256 random things, like one of them will be best, sure, I got that. But
Yeah.
like, is it like statistically unlikely? Like I don't understand.
Yeah, okay, so I mean, so basically the only takeaway from here is mixing also matters for VLMs. That's why it's a very short section in the paper. Yeah,
that was it.
Yeah, that's it. Like you don't. I'm not saying there's a way to find a good like. It's basically just to show Mixtera works for VLMs.
Okay.
And to show, yeah, you don't need to materialize the data set also for VLMs with Mixtera, and to show it has impact on downstream performance. But exactly, like, okay, you know, everybody can generate a lot of mixtures, and then one of them will work best. So that's totally true. It would be interesting to look into ADO for VLMs, sort of like my next step with the system. I think the main issue is the token count that sort of is imbalanced across modalities. Because yeah, if you think about scaling laws and of that stuff, if that's based on token count, you might have issues. Might have need to adjust the algorithm slightly.
So I think we're a couple minutes over.
I'm not like
Okay,
yeah,
great.
I'm done basically anyway. So
Oh wait, I wanted to see the
yeah, okay. Well, you're in one of the next meetings, so if you want to see it, then that's fine.
But I guess that's the most important.
Yeah,
the
Right? Like,
throughput,
is it faster or not?
so takeaway is, yeah, all of the data loaders, they somehow they scale up with Mixtera. You see a little bit of a variance. It's mostly because this is like a very small model, like a 200 M model on a GH200. So this means there's no compute bottleneck at all here. So this sort of stresses the data loader like quite a lot. So if you use 4 workers, like even for this like let's say extreme or hardcore scenario, right? Mixtera basically gets to the same throughput as like sequentially reading. Obviously, the big struggle is the non-sequential reading, which is why you see that variance like in the error bars for like a low number of workers, because sometimes we need to load an entire file and just read a single sample. But if I would show you this plot on a, let's say, 3B model, you wouldn't even, like, you probably won't even see those error bars. This is like a tiny model on a very fast GPU.
Okay, so
Cool.
one question is like, so why should someone use Mixtera over like standard loading, like just like big picture, like if it's similar performance, like what's the upside, like the adaptive optimization perspective?
A, dynamic mixing, and B, it avoids, it makes your iteration a lot faster, so you don't need to
You
materialize.
don't need to run a goddamn every time you want.
You can like do the experiment like.
Yeah, so basically you can just like get
Reliability
all of the
and
quality scores for every single sample. You'll get like every single feature you care about, and then just run the experiment at the data.
For example, for Mosaic, like how did you compare it against Mosaic? Like you, for example, you prepared the data beforehand for every single experiment here, or?
Yeah, so right, all of them run on the same data, right? The same stored on the same DFS, and we just measure the throughput when iterating, or like the throughput over.
For example, for this plot, it's not dynamic mixing, right? It's only the throughput. Because it's not supported by Mosaic, for example.
Yes. So this is like just static mixing, right? So this is Mosaic doesn't even use a mixture in this case. It's just one file reading how much. So this is also why I don't think this is the most interesting experiment ever. It's like also this, right? They all sort of, especially the data loaders that just linearly go through files. There's not a lot of magic happening there. I think it just reads files and goes on to the next.
Basically, this comparison doesn't use any of the features that
Exactly.
make Mixtera special. It just shows that with those features, Mixtera still gets the performance.
Yes, and maybe last to end this. So Mixtera, why would you use Mixtera? I mean, beyond dynamic mixing and this iteration, maybe lineage tracking or like provenance is interesting to you. We don't have like I haven't engineered those features, but if you have a query, right, you can associate it with the model, and if you do that and run some evals on your model, what I think is sort of like the next step is to like do some sort of matching between these mixtures perform really well in my ablations or something. And then to see, these 10 mixtures perform really well, what do they have in common? Because, for example, speaking to somebody from Hugging Face, they told us 10-second videos performed really well for their VLMs, and it took them like a month to figure out why those mixtures were working really, really great. So if you have something built on top of Mixtera that keeps track of statistics, that would be another like thing I think it's really interesting. Like get close to feedback, close to eval feedback loop to the mixture, basically. Yeah. So
Are you working on that or who's working on that?
and I want to work on that.
Oh, you want to work on that.
Basically. It's like the next step. So yeah, thank you so much. I'm sorry for taking much.
No. We had hundreds of questions. That was awesome. Thank you. I think the quality here is pretty obvious. And I think not having to write out a full data set for every experiment you want to do is a pretty appealing concept.